Hi Chem 240 students, this is Dr. Ricardo. We're going to do chapter 17, video number 4. Starts on page 24 of the notes. And the first topic is precipitation calculations. So these are the calculations that you use using the KSP to figure if you take two solutions, both of which are soluble, and then you mix them together, are you going to get a precipitate or not? So instead of taking the salt and just dissolving it in water or trying to dissolve the solid salt in a solution with a common ion, you're basically taking two solutions that neither one of them forms a precipitate. So I'm going to give you a classic example quickly, and then asking yourself, if I put these two solutions together, is the new solution going to form a precipitate or not? So a classic example would be to take a solution of silver nitrate, right? Because all nitrates are soluble. So this thing would be a clear, colorless, beautiful solution, right? And then I'm going to add it to another solution. I'm going to make this one smaller just so I have enough room to pour this one into this one. I'm going to add it to another solution that's also clear, colorless, beautiful solution. And in that case, it's going to be regular table salt sodium chloride. Okay, so I have four ions that could potentially get together, right? Silver is already with nitrate, it's already soluble. Sodium is already with chlorine, already soluble. These things have KSPs that are not even a factor, right? They're going to be numbers that are greater than 1. You're going to be able to put huge amounts in, not tiny amounts. But when I take this, well, actually, let me add this one to this one because it's smaller, okay? When I add this one to this one, well, first of all, I do have to take into consideration the dilution. So the fact that now all four of these ions are going to exist in a bigger amount, whatever this is. So let's say this is a certain V1, right? And this is V2. What do we have here? V1 plus V2 is the new volume. Okay, so the volumes are always additive. So the question is, do we get a precipitate? Well, that's going to be based on the concentration of this and this. So first of all, you should remember that there is a single replacement reaction that occurs when these two things get together, right? And double replacement. This guy potentially could react with this to make AgCl solid, which it does because the solubility product constant for silver chloride is a very small number. And then the other one, sodium with nitrate, is definitely soluble. The KSP is a huge number. So there's no question that this guy is going to stay soluble in solution. So when I put these two things together, do I get a precipitate or not? Do I see white crystals form and then slowly head to the bottom, right? This thing, two clear colorless solutions that look like water, mix them together. If there's enough concentration of silver chloride to exceed the solubility of silver chloride, then what I'm going to see is this thing is going to look like snow because there's going to be so much white precipitate or milk. And then I would either put it in the centrifuge to get it to settle to the bottom or just wait a certain amount of time. If I wait a certain amount of time, sorry, my beaker changed the shape, the silver chloride will settle out on the bottom. I'm going to have mostly sodium ions here and nitrate ions. I'm going to have a huge amount of those, but I will have a little bit of silver chloride in here, right? Just enough to saturate that solution, but that's going to be tiny next to this. So in most cases, even the tiniest amount of sodium chloride added to a silver nitrate solution would form a precipitate, or the tiniest amount of silver nitrate added to a sodium chloride solution would form a precipitate. Why? Because the KSP for this thing is tiny. Okay? So how are we going to tell? Well, what we're going to do is we're going to compare the ion product, okay, which is the Q value, with the KSP. So let's talk about the definition of the ion product. So the ion product QC, and we saw this back in chapter 15 when we talked about QC for equilibrium expressions. It's really the same thing. So the ion product is the product of the ion concentrations in solution. Each concentration raised to the power equal to the number of ions in the formula of the ionic compound. So if a compound, M3X2, is going to break up into 5 ions, right? 3 plus 2 is 5. It's going to be the initial concentration of the M to the third power times the initial concentration of X to the squared power. Why is that? Because that mimics what the KSP looks like. The difference is QC is based on initial experimental concentrations, what you put together. So after this gets added to this, and I know the total volume, all I have to do is take care of the dilution, right? Let's say this was 90 milliliters and 10 milliliters. Now I have a total of 100 milliliters. And if I can just factor in the fact that this solution now was diluted a little bit, if I knew the original concentration of this and the original concentration of this, I'd know the initial concentrations and I could see, have I exceeded the solubility limit? If QC turns out to be less than KSP, then my solution is unsaturated. I have not maxed out the total amount of silver ions and chloride ions that the solution can hold. If QC is equal to KSP, it's exactly at solubility. Don't have any extra, right? And if QC is greater than KSP, then boom, I'm going to get a huge amount of precipitate out and the solution will remain saturated on top of it. So we're going to compare these QC values with KSP. Again, these are initial concentrations after the solution has been mixed but before they start to react versus the equilibrium concentrations. Okay, so let's take a look at a problem. So M3X2 solid breaks up into 3 M plus 2s and 2X minus 3s. You wouldn't have necessarily, didn't have to be those charges, but that's usually what's going to happen because how do we get positive 6 and a negative 6? Usually it's 3 times 2 and 2 times 3. Right? So let's just read through these notes and then we'll go from there. If QC is less than KSP, precipitation will not occur and the solution is considered unsaturated. If QC is greater than KSP, precipitation will occur. You have a saturated solution, the extra precipitate will fall to the bottom. If QC is equal to KSP, this is hard to do to get just the right amount in there, the solution is just saturated. No more salt can be dissolved without forming a precipitate. So you can't add anything. Not only could you not add any salt to the bottom, you couldn't add any of one of the common ions, right, from another source. So you couldn't add any extra X minus or M plus. If you did, either of these would push it to the point where more solid would form. Okay, so you're actually at the breaking point if QC is equal to KSP. You can't do anything to it. Okay, next thing we're going to talk about is how does pH affect solubility? Well, the way pH affects solubility is if one of the ions that dissolves happens to be either a weak acid or a weak base, or the conjugate acid of a weak acid or conjugate base, the conjugate base of a weak acid or the conjugate acid of a weak base, then not only is it going to be involved in the precipitation reaction, it's also going to be involved with an acid-base reaction. And that's a neat thing because it's going to be a way, kind of like Le Chatelier's principle, to remove the common ion from the solution so that more can dissolve. Or you can force it to precipitate because you're adding a common ion. So let's take a look at it. It's sometimes necessary to account for other reactions that the ions might undergo. If the anion, the negatively charged ion, is the conjugate base of a weak acid, it reacts with H plus or hydronium. Okay, so you should expect the solubility to be affected by pH. So let's take an example. Okay, here's the KSP expression. Okay, or I should say the reaction for calcium cyanide. So calcium cyanide ion is only slightly soluble. Its KSP is going to be a small number. Let me see if I give it to you. Actually, I just do this qualitatively, but let's assume it's something like 10 to the minus fifth or higher. Or smaller than that, right? So 10 to the minus 6, 10 to the minus 7. So small number means only a little tiny bit is going to dissolve. Okay, so first reaction is the precipitation reaction. So if I put calcium cyanide on the bottom of a beaker and I add water to it, it's got to go to the right. It's going to make a little bit of this and a little bit of this. You get twice as many cyanides for every calcium cyanide, right? Okay, well, the cyanide ion, as soon as it hits water, it's going to react with any excess hydrogen ions around or react with water in the hydrolysis reaction, and you're going to remove cyanide ions, right? You're going to remove cyanide ions by pushing this second equilibrium to hydrogen cyanate. So you're taking this away. So by Le Chatelier's principle, they're removing the cyanide, more will react. So the lower the pH, the more calcium cyanide that you will be able to get into solution. So if you want to dissolve more calcium cyanide into solution, let's say you really want to get rid of your someone, right? So cyanide is the famous poison, very dangerous stuff to work with. You don't want to ingest this in any way, shape, or form. If you were going to work with this stuff, you would definitely work with it with gloves on. Okay, so calcium cyanide should be more soluble in acidic situations than basic situations. Okay, all right, here's another example. Here's the precipitation reaction. This is only a slightly soluble salt, calcium hydroxide. Well, obviously, look, the hydroxide is directly in there, right? So the calcium hydroxide, as it dissolves, is going to make the solution very basic. Well, if I add hydrogen ions from an external source, right, like for instance, add lemon juice, add vinegar, well, the hydrogen ions are going to react with the hydroxide ions to neutralize them and make water. So you're going to be removing hydroxide ions from solution. So what would happen by Le Chatelier's principle? You'd get more to dissolve. So here's another example of this would be more soluble in acidic solution than basic solution. Why? Because this common ion is involved in another reaction. It's involved in the neutralization reaction. So lower the pH and more will dissolve. How do you lower the pH? Add a different acid that has nothing to do with this. Add HCl, right? Or nitric acid. Okay, those would be the two best ones because all nitrates are soluble and chloride is pretty soluble with everything. You don't want to form the different precipitate from the common ion from after the HCl. You want to deliver the HCl, but you don't want to be worried about, okay, will chloride form a precipitate with calcium? Well, you don't have to worry because that one is insoluble. And the best guy to use, if I had to try to get something into solution and I wanted to add external acid, I would add it in the form, instead of hydrochloric acid, I would add it in the form of nitric acid, because this guy gives me the H plus I want, but the counter ion is not only not a strong base, right? It's a terrible base because this is such a fantastic acid, but this is the universal solvent. This is soluble with everything. So you don't have to worry about it precipitating with calcium. All right, so calcium hydroxide should be more soluble in acid than it is in base. Okay, let's read the last note here. What is the expected pH effect on calcium carbonate precipitate in equilibrium? Okay, so now this is an important one, right? Because the carbonate we know is in a very important buffer solution, but if I had any kind of a soda water or anything like that that has carbonate in it, I can drive this precipitation reaction to get totally dissolved by changing the pH. Why? Because carbonate also reacts with water to make hydrogen carbonate, and then hydrogen carbonate further could react with water to make carbonic acid. So let's take a look at that. I'll show you that pretty quickly. A different sheet of paper. So here was my precipitation reaction, right? I had how much calcium carbonate could I get to dissolve? It's definitely going to be a function of pH. Why? Because this equilibrium, this is the KSP, right? KSP is equal to the calcium ion concentration times the carbonate ion concentration. Okay? But This is a common ion, right? So I can remove this from solution by doing what to it? Well, I could do it by adding external hydronium ions to it. So if I add external hydronium ions to it, the first reaction that will happen is this is going to go pretty far to the right. This is a neutralization reaction. This wants to happen, right? Because K2 for this is a very small number, so this is pretty basic, okay? So this guy is going to go make hydrogen carbonate back and water. So that's a neutralization reaction. Okay? So I'm removing the carbonate by lowering the pH. So what would happen to this? At low pH, I would be able to dissolve a lot more calcium carbonate into the solution than I would be just in water, okay? Because it participates in this second reaction. You can actually, I'm not going to do it, but you can actually put these two reactions together and see what is the K value. You take the KSP for this, right? And the K, this guy would be neutralization. You put those two together and see what would it be for the overall reaction, because this guy would cancel out, and I'd have this plus this to give me this, this, and this, right? So that's kind of neat, right? And you can see that that reaction would probably be pretty high equilibrium, right? So you can get a new equilibrium by putting these two together. Add these two together, multiply their equilibrium constants, okay? This one, be careful, this is not a KB, because this guy's over here. The KB would be if you just had water plus this, right? To give you this plus hydroxide. Okay, but you can get this pretty easily too. All right, let's keep going. Page 26. This is kind of neat. There's a technique that you can use to separate metal ions by forming sulfide precipitates. Okay, so many metal sulfides are insoluble in water at pH 7. Okay, but if you dissolve them in acidic solution, it changes the solubility of the pH. Let me start reading this again. Sorry about that. So many metal sulfides are insoluble in water at pH approximately 7, but dissolved in acidic solution, the changes in solubility with pH can be used to separate the mixture of metal ions. Okay, so let's take a look at this. What you could do is bubble H2S solution, and this is something they do at the water treatment plant. Okay, this is one very useful way to get the metals out of the water before they recycle it and put it back into the rivers or wherever that you were putting the water. Okay, so the maximum solubility of H2S at 25 degrees is 0.1 molar. Okay, so if I continuously, this is kind of neat, if I continuously at my water treatment plant take the effluent water after all the other steps have been done, so you've done the disinfection, you've done all the other initial steps, you've done all the biological steps to get the organics to react, now you bubble H2S through the solution. Okay, so this H2S concentration is going to stay at 0.1 based on this equilibrium. Okay, that's the maximum I can put in there. Okay, so if you solve the Henry's law constant for this, you get 0.1 if you solve for this guy over here. How much stays in solution? Okay, you know the Henry's law constant, and you know the pressure that you put on it. The maximum you can put is 0.1. All right, now, cool thing is H2S goes through two equilibrium. It's a weak acid, so it's first Ka1 for the dissociation into H+, and hydrogen sulfide ion is 8.9 times 10 to the minus 8, so very weak acid. Another way to look at it is this plus water would give you hydronium plus hydrogen sulfide. How does the second hydrogen come off? Well, that's not really super significant, because the second one comes off to much smaller degree, which is very typical, right? 10,000 times smaller. This is 10 to the minus 13th. This is 10 to the minus 8th. So 5 orders of magnitude. It's actually 100,000 times less important, right? Goes 100,000 times less to the right than the first one. Okay, but it can come off. Okay, so comes off, you make another H plus, and you make sulfide ions. So if you put the two together, you get the overall equilibrium constant. Add up the two reactions. These two add up. This intermediate cancels out, and I get this decomposes to give me the two H pluses plus S minus 2. Now remember, you could have also rewrote that like this. Anytime you have a reaction, you can either show it in the very simple, high school chemistry way of it just decomposing, or for us, we would react it with two water molecules. Nothing would change, right? My equilibrium constant is going to be the same to give me, if both of these guys are able, one of them comes off, protonates the first water molecule, second one comes off, protonates the second one. I'm going to get two hydroniums and sulfide. Okay, so this Ka over here, right, just adding water to each doesn't change anything. This guy has the same exact Ka. It's just looking at it in a more sophisticated form. Kind of like it better, right? So what's the overall Ka for this guy or this guy? Tiny, 1.2 times 10 to the minus 20th. So what are we going to do? We're going to have to drive the pH down very, very low as a mechanism to take the sulfide out of solution and selectively, based on pH, get each metal to come out separately, collect it, then lower the pH some more, get the next one, lower the pH some more, until you get to the one that's the hardest to get out. Okay, very neat idea. Okay, so all I'm doing now is I'm going to rearrange my Ka expression, and I'm going to plug in the number at 25 degrees. 1.1 times 10 to the minus 20th is equal to H2S, H plus squared times sulfide divided by H2S. But we know this denominator, if I keep bubbling the water in, I can keep it at 0.1. Right? So I'm going to leave my 0.1 in there. I'm going to get this really cool, neat little expression that the overall Ka is equal to the hydrogen ion concentration, this is a function of pH, times the sulfide ion concentration divided by 0.1. Rearrange this, bring this 0.1 up here, and you'll get, as long as you keep bubbling the hydrogen sulfide through water at 25 degrees, right, at the water treatment plant, the hydrogen ion concentration squared times the sulfide ion concentration will always be equal to this number. Solve this for S to the minus 2, right? Solve this for S. In this case, if I do that, this hydrogen ion concentration is going to go in the denominator. And last case, how do I solve this for hydrogen ion concentration if I wanted to calculate the pH? Well, take the same expression, move the sulfide underneath, and take the square root. Okay, so these are two ways of looking at it, right? So that's the equation we can, as long as we're bubbling hydrogen sulfide gas through the solution, this will always be true, and this will always be true. So by adjusting the pH, we can control, right? We can control the amount of sulfide ions that are dissolved. And therefore, if we have less sulfide ions dissolved, more of the metals can stay in solution. Okay? All right, so let's take a look at this. Number 5. Consider a solution of that's 0.1 molar in zinc plus 2 and 0.1 molar in lead, okay? And plus 2, okay? So water treatment plant, somehow there's an industrial process and the wastewater is coming in and it's 0.1 molar in zinc and it's 0.1 molar in lead. Now before I discharge this water, I need to get the lead and the zinc out. Well, I can get them both out together, right? And then I'll just get this precipitate that's going to have zinc and lead sulfide all mixed together. Or I could be smarter than that. I can serially adjust the pH, do one at a time, knock out one, collect the precipitate at this first pH, then move that solution over, right? Get it off of the solid, then change the pH, get the second one to precipitate out. So here's the question. What pH range will give a precipitate of one metal sulfide leaving the other metal ion in solution? Sorry, my screen went off, guys. I'll just get it back on. Okay. So here's the two KSPs. So the two KSPs, the KSP for zinc sulfide is 1.1 times 10 to the minus 21st. For the lead sulfide is 2.5 times 10 to the minus 27. So which one is going to come off first? Okay, which one is going to come off first? Well, the zinc should come off first, right? Because look at that number, that's tiny. So you're going to be able to, it's going to be easier, right? You're not going to have to go to such dramatically low pH to get this guy out of solution versus this guy, right? So I think that's what's going to happen. Let's take a look at what the pH range is. Okay, now what are we going to do? I'm going to copy these two things on the other piece of paper so we have them for the next step, right? If I need to know what's the sulfide ion concentration, I'm going to always remember, I keep my bubbler on. This is always true. Or I think what we're going to have to do is if we want to know what hydrogen ion concentration, what pH, I'm going to just take my 1.1 times 10 to the minus 21st and divide it by whatever the sulfide ion concentration is. Okay, so we'll keep those handy. We'll see which one we're going to use. Okay, so what I did here was I did one on the left for zinc sulfide, one on the right for lead sulfide. So I did them in parallel with one another. Okay, this way you can see the difference. Okay, so there's enough space for both. All right, so first of all, first thing, let's write the KSP reaction for zinc sulfide. So zinc sulfide is in equilibrium with zinc plus 2 and sulfur minus 2. KSP, which we have, is equal to the zinc concentration times the sulfide ion concentration. Okay? So what do? We want to solve this for the maximum amount of sulfide that could be in solution. We know the zinc because in the question they told us we have 0.1 molar zinc. So we want to see what pH do I need to go to get this zinc sulfide to precipitate. Okay? So the maximum amount of sulfide that can stay in solution is going to be KSP divided by 0.1. So that's the sulfide ion concentration. Well, guess what? Sulfide ion concentration is directly related to hydrogen ion concentration as long as I keep the bubbler on. So if I rearrange it, this is the one I'm going to use. The question is, what pH will deliver that amount of S minus 2? I solve this for the hydrogen ion concentration. So over here, I get my S to the minus 2 is going to be 1.1 times 10 to the minus 21st divided by my 0.1, right? So I have my S to the minus 2, and now I solve. This is the minimum amount of hydrogen that I need, the minimum amount of hydrogen that I need to get the 0.1 molar zinc sulfide to all dissolve. Okay? Solve it for hydrogen ion concentration, I get a huge number, 0.32. Okay, if I have the hydrogen ion concentration, I can always get pH. This is the minimum amount of hydrogen ion concentration that I can have in solution. So what's the maximum pH that I can go to, right? If this is a minimum, pH works opposite. This is going to be a maximum. Take the log of this, it's going to come out to negative 0.5. Log base 10, it's going to come out to negative 0.5. Throw away the negative sign. The maximum pH that I can go to before zinc sulfide would precipitate out of solution is 0.5. So it's going to be insoluble above pH 0.5. So I have to keep this in extremely high pH solution in order to get the zinc sulfide to stay in solution. Okay? Hydrogen ion concentration is 0.32. The pH is 0.5. Okay, let's do the parallel calculation. The only difference between this one and this one is the KSP. Zinc is even going to be harder to keep in solution. You're going to have to go to even a higher amount, right? Even a higher amount of hydrogen ion concentration, and even a lower pH to keep it in solution under those conditions. Okay, so let's go through the analysis. KSP is equal to the lead concentration times the sulfide. Solve this for lead. Since I'm bubbling my hydrogen ion concentration through, and I know that I'm bubbling H2S, this number over here, this 0.1 comes from the fact that if my solution is 0.1 molar in lead plus 2. So what's the sulfide ion concentration at equilibrium? Solve this for hydrogen ions. H plus then is equal to the square root of 1.1 times 10 to the minus 21st divided by S to the minus 2. I wind up with a hydrogen ion concentration of 210. You can't fit that many hydrogen ions in a liter of water. Remember, the molarity of water in water is 55, right? So there's not enough water molecules to put hydrogen ions on to make hydronium ions. The most you could make is 55 molar. If you protonated every single water in a liter of pure water, the best you can get is 55 molar hydronium or 55 molar H plus. So this is impossible. So what does that mean? That means that the pH, sorry guys, I just got distracted. So that means that the pH of 210 is negative 2.32, right? So again, can't go that low. I don't even care. Sulfuric acid, there's no acid that you can get a pH that's low. So this is going to be insoluble at any pH. The zinc is going to come out at 0.5, which is possible, a pH of 0.5. The lead is never going to come out. Okay? So here's how we do it. How do you get one out and keep the other one in? So you have your solution. Okay? You have your solution. It's coming out of the wastewater treatment plant. We know it's 0.1 molar in zinc plus 2 and 0.1 molar in lead plus 2. Right? I want to selectively get these two things out. Okay? So first thing I could do is I start to bubble the H2S. When I bubble the H2S through the solution, both of them are going to precipitate to the bottom. Going to knock them both out. I'm going to have my zinc in the form of sulfide, and I'm going to have my lead in the form of sulfide. Okay? All right. Now, this water, all of the zinc and all of the lead are essentially, the concentrations in here are tiny because the S minus 2 is such a large number that the amount of zinc and lead, which is lead is the one you're worried about, that's in here is going to be insignificant. So this water then can be removed and dumped into the river. It would be safe. Okay? Now you take this precipitate and you add strong acid to it. As long as the pH is below 0.5, the zinc will redissolve. So you, in a strong acid solution, I could take my solid down here, add strong acid to it, and the zinc would go back into solution. So now I would have a solution that would have the zinc plus 2 in it, leaving behind only the lead sulfate, which is the dangerous stuff. The zinc would be valuable. You could sell it. Well, the lead you could use for something too, but you want to separate them. Now you get the zinc plus 2 back into the solution, right? Keep the H2S gas on it, right? But as long as the pH is lower than 0.5, the zinc will redissolve. You take that acidic solution of zinc, move it over to another tank, raise the pH, and the zinc sulfide will precipitate over here. When you pour off this acidic solution of zinc sulfate, the zinc is in solution. It'll leave behind a solid that's just the lead sulfate. So this is a kind of neat example. Okay. So let's read what we have at the bottom here. When saturated with H2S, any solution of 0.1 molar zinc and 0.1 molar lead in which the hydrogen ion concentration is greater than 0.32 will give a precipitate of lead but not a precipitate of zinc. Okay, and how did we get that? We substituted in for the KSP, for the sulfide ion concentration, first of all, 0.1, and then this expression here, which was related to the Ka of H2S. So this all down here is substituted in for s to the minus 2. That's this thing over here. Okay, and where did this come from? This came from a couple of different places, mostly the fact that S minus 2 is not only in an equilibrium with the metal ions, a precipitation equilibrium with the metal ions, it's also in an equilibrium with hydrogen ions to make back the H2S. Okay, so if I can swamp this with hydrogen ions, then I'll have all of the sulfide will be in the H2S form. If it's in the H2S form, there won't be enough around to precipitate with either of the metals. Okay? There's no concentration in the case of zinc that you can go to, that you can't put so much acid in to get rid of the sulfate to the point where the zinc would come out of solution. Where the lead would come out of solution. But for the zinc, all you have to do is get to pH lower than 0.5, right, which is possible. Get to a pH lower than 0.5, very acidic, but possible. And at that point, the zinc will go back into solution, leaving the lead sulfate by itself. Okay. And the last way that you could look at it up at the top here is if you want to know what the metal ion concentration is in a solution where you're bubbling 0.1 molar, where you're bubbling H2S through the solution, you take the KSP of the metal times the hydrogen ion squared divided by 1.1 times 10 to the minus 21st. So the higher the hydrogen ion concentration, the more the metal that's going to be able to be dissolved. Okay, in lead, in the case of lead, right, you want the amount of lead to be tiny in any water supply. So let's do that calculation. So I'm going to take the lead number here, okay, and let's see, in a water supply, if I bubbled H2S through it, what would the lead concentration be? Because that's the dangerous element in places like Flint. It was the lead that's doing the poisoning. So what would the lead concentration be if I release the water at pH of 7? Okay, so pH of 7, right, corresponds to hydrogen ion concentration or a hydronium ion concentration of 10 to the minus 7th. Everybody's good with that, right? So that's what's going to get plugged in over here. Let me look up the KSP for lead sulfide. All right, we need to get the lead out of the water. So the KSP, I think that's 2 pages back. The KSP for lead sulfide was tiny. Good. The smaller the better. So this is a very good way to make sure that you've gotten all the lead out of the water before you release it. Okay, so this is the given KSP for PBS solid. Okay, so that's that. I just looked it up at 25 degrees. Hydrogen ion concentration, pH 7, 10 to the minus 7 squared. Look at this number, guys. 10 to the minus 27th divided by 10 to the minus 7. This is going to give us another 10 to the minus 14th. All right, those are all good because we want this number to be low. Well, the denominator we're stuck with. Where did the denominator come from? Came from two facts. I won't overdo it, but came from fact number one, that the maximum amount of H2S that can be dissolved in solution at any one time is 0.1. Second fact, that S minus 2 is not only involved in this equilibrium, it's involved in the overall Ka of H2S. So the amount of S minus 2 is very small. Let me give you that Ka, the overall Ka. All right, the overall Ka, capital A, for H2S to lose both of its protons and make sulfide minus 1 is 1.1 times 10 to the minus 20th. And there's only one more fact that we put together here, is that if we keep the bubbler on, right, from the Henry's law constant, the concentration, I can make a 1 molar solution of H2S aqueous from a saturated solution. It's the most you can put in of H2S gas. So keep the bubbler on, keep bubbling it in. This guy will be 0.1. So those three facts create this number here. This guy, and these two I should say, create this number here, right? 10 to the minus 20th times 0.1 gives you 10 to the minus 21st. Okay, so let's do the calculation here and see what is the maximum amount of lead that would be coming out of the wastewater treatment plant if I did this process. I bubbled H2S through the solution to knock down all of the lead to make lead sulfide precipitate, and I made sure that I did not, after I did that at pH 7. Okay. So I'm going to do this 10 to the minus 7 squared is 10 to the minus 14th. So I have 2.5 E minus 27 times 1 E minus 14. Okay, wow. That gives me 2.5 times 10 to the minus 41st power. Okay, now got to take care of the denominator. Divided by parentheses 1.1 E minus 21. That's the denominator. Boom. Okay. Well, I get 2.27 times 10 to the minus 20th moles per liter. All right, now we could convert that to parts per million pretty easily, right? Parts per million pretty easily. We know the molar mass of lead, so let's go ahead and do that down here, and we have an idea of how much lead would be going out to the public, right? Is it going to be well below the concentrations that are allowed, which are on ppb levels, parts per billion levels? Okay. All right, so I have 10 to the minus 20th, and this is moles of lead. That's the thing I care about, the lead plus 2 per liter. Okay. All right, so the first thing we're going to do is let's convert this to grams of lead. Right, so there are 207 grams, this is from the molar mass of lead, in every 1 mole of lead. That'll change the numerator from moles of lead to grams of lead. Okay, then I just have to change the denominator. So I get 207 times 2.27 e to the minus 20th. Okay, now I have 4.69, so 4.7 times 10 to the minus, let me get my light on here, 10 to the minus 18th. 4.7 times 10 to the minus 18th grams per liter. Okay, last step. If I want to compare things, I need grams per every 1 million grams of this. So if I make an easy assumption, right, in this water solution, it's pretty much water that we're sending out to the public, 1 liter of water, because this is grams per liter, is equal to 1,000 grams of water. Okay, and where does that come from? The density of water is equal to 1. 1 liter would be 1 kilogram. So I'm going to change my denominator for every 1,000 grams. So now I have 4.7 times 10 to the minus 18th grams of lead. This is per PB, divided by each 1,000, which is 10 to the third grams of solution, grams of water. Okay, so I want to get parts per billion. Let me first, this right now is parts for every 1,000, right? So this is parts per 1,000. So if I want to get to parts per billion is milligrams, milligrams per kilogram is parts per billion. So wait, I'm going to go back to here, 4.7 times 10 to the minus 18th grams of lead for every 1 kilogram. Okay, so I'm just going to take something that I know. This is ppb. ppb is micrograms per kilogram, right? Because this is a millionth of a gram, and this is a thousandth of a gram. So the relationship between here and here is 1 billionth, right? So I got my denominator straight. How do I get to micrograms? Well, micrograms is 10 to the minus 9th, right? 10 to the minus 6th. So if that's 10 to the minus 6th, I want to get the top to micrograms. I can say that there are in every 1 gram, there are 10 to the 6th micrograms, 1 million micrograms in a gram. So grams cancel out. 18, take away 6 is 12, right? So this is going to be 4.7 times 10 to the minus 12th micrograms per 1 kilogram. And micrograms per kilograms, guys, is parts per billion. So tiny, tiny amount. You can release this to the public. The amount coming out of the wastewater treatment plant is going to be 4.7 times 10 to the minus 12th parts per billion, ppb. Okay, what's the regulated amount? Well, you can't put anything greater than like 0.1 parts per billion into the water stream for people to drink. So this process would work great. And this is actually one process that they do at the wastewater treatment plant to knock the lead out of the water, right? Form sulfides solutions with it. Okay, and H2S is easy to get. Okay, all right, gonna stop right there. This video turned out to be a little long. This whole last section is not really kind of testable stuff, but kind of neat if you want to think about water treatment. Okay, you can look up more about it.